Hello everyone. I'll be talking about decoding the black box, understanding the Go compiler. So I just firstly want to understand how many of you are familiar with Golang or have worked on Golang. Oh, cool. Only 1%, 2 or 2%, 3%. Cool. So I'll start with the basics of a compiler, irrespective of Go compiler, or if it's a Java compiler or C++ compiler. But before proceeding with that, I'll just talk about me. This sums up pretty much my professional life. Right inside is the previous works which I have done, involvement with the communities, or I have worked with the Gojek. I've been a part of Mozilla community for a long period of time, since 8 years almost. And currently I work as a senior software engineer at Fold, and which is a fintech startup. And apart from that, I'm a Docker captain, and I also run Women Who Go Bangalore chapter. Now let's proceed with the actual topic, decoding the black box. So what happens when you write a code and you run go build, right? In Go, you use go build to compile your code. So I'll just focus on that part. So if the source code is your input, right? So in that part, once the source code is being passed to the lexer, or basically scanner. So this is the third part. So lexer actually reads the source code file, and finally it converts it into the tokens. So if you see, tokens are the very small, you can the smallest unit of meaning, and it is also known as scanner. And everything in your code gets scanned by lexer, and then it get converted into the tokens. And that tokens could be something like keywords like if, else, or inbuilt statements, right? So those are the identifiers, literals, or operators. And at this stage, at lexer stage, it also discards the white spaces and the comments. So whatever the comments you provide, right, in your source code file, those are also discarded during this stage. This is one of the first stage which happens during your compilation. Next stage happens when lexer produces the output to the parser. Parser ultimately consumes the output of lexer, and it creates those tokens into the AST. AST is basically a syntax tree, so abstract syntax tree. So at this level, your syntax tree gets created or constructed, and you can say that it's a grammatical representation of any program. So all the tokens which were created during the lexer phase, right, they will be compiled or assembled into the AST form at this stage. And what will parser will do, it will check the code base against the grammatical rule of your programming language. It could be Golang here, it could be Java, it could be C as well. So that it just ensures that your program has been structured correctly. For example, if you haven't used semicolon in Java, right, it will be thrown at this level. So in Go, it doesn't matter right now, it's optional, but it by default it added the semicolon. So in Java, it will be added at this level. And after this, parser will produce the AST, abstract syntax tree, which will be used in semantic analysis and time checking phase. So in this process, what happens, AST is like being checked. You can think of it as a way like a building inspector is there, and that person has come just to see how your building looks like as compared to the blueprint. Blueprint, you can say AST is one of the blueprint, and also based on the regulations as in rules and regulations of your programming language. So this phase ultimately involves checking the AST programming grammatical rules, and also how you are adhering to the grammatical rules of any language. In this context, I'm talking about Go. And it also ensures that operations are performed on the compatible types. For example, if you are using integer or instead of a function, it will throw error at this level. So in this stage, those kind of errors would be being detected, and compiler will halt the compilation process immediately at this stage. So next one is after the type checking and semantic analysis, what happens is the code intermediate code generation happens. What happens is intermediate code generation, you can say it is as intermediate representation, which is actually a lower level representation of your program. The program which you wrote, the source code, it's actually gets converted into the intermediate representation, and through the translation of AST into the sequence of instructions. And it is independent of the target machine's architecture. So any code, the source code is getting translated from tokens to AST tree, and then finally back to the like intermediate representation. These are all part of the these are all are platform agnostic. So it doesn't matter on which target machines your architecture would be, it will just perform the operations automatically, and it serves as a middle ground between the lexer and the optimization of the final output, so as to make the optimizations more better. At this step, after the IR, intermediate representation, has been generated, now next step is optimization of that IR. So at optimization level, what happens, why we do it is because of we want to make the compilation more effortless, efficient, and faster. So at this step is quite important because there are two ways to do that. One of the methods is SSA, which is basically static single assignment. In this, each variable is uniquely assigned. So Go compiler maintains that, and through this, data dependency is also excluded. So in turn, what happens is the compilation becomes more smoother, faster, and efficient. And for example, like, there are different techniques to do the optimization. One of them is like eliminating unnecessary calculations, or reducing the number of instructions, so or reducing the memory uses. So those kind of optimizations compiler will do at this stage. And SSA is very important in this context. And after the optimization, the optimized IR is converted into the machine code, which is actually your binary statements or instructions, which are ultimately be understandable by your processor. So at this stage, as I mentioned, this phase converts the optimized IR into the machine code and the binary instructions that your processor understands ultimately, right? And so all the instructions which were written in the IR are mapped directly to the binary instructions in this phase. And if you remember, I previously mentioned that all the previous stages, they were platform agnostic, but this stage is not platform agnostic. In this stage, during the translation itself, the specifics of the target machines are considered, as for example, number and types of the registers. So those are being considered while doing the compilation. So this happens at this stage. In previous stages, the target machine's architecture was not considered at all. So this one is the last stage, I would say, where we link all the code with your binaries. So it is the final step, and different pieces of your generated machine code are being clubbed into single executable file, which also includes your binary. So in Go, what happens is there is a static linking happening. What does it mean? Basically, in Java, it's a dynamic linking. You can think of it a way. So your application will have some dependency libraries, right? So if you compile all of them into one binary, that happens in Go, which is called as static linking. But if in the external libraries are being compiled, they are not included in the single binary. Those are called as dynamic linking. So linking has to resolve through the undefined symbols and all. So your program will ultimately be structured in a way that this function is linked at this so and so place, and hence it will be faster ultimately. So it happens at the compiler phase itself, and every dependency in Go is included in the binary, which ultimately makes the Go compilation process faster as compared to Java or C++. And once the linking is completed, you get an executable file that is getting operated on the that is getting operated into the memory, and CPU can execute it. Yeah, this is the last step. So I've mentioned in this way. And if you want to get started, or if you haven't worked with it, just add a log statement or add a panic statement just to understand the insights. And compiler also provides some logging and debugging visualization capabilities. This is how in Go you can have logs. You can see how, you can see the flags. You can generate the print the assembly. You can also do the internal parse tree. You can create actually internal parse tree to such commands, and these are inbuilt things in Go. And these are the additional tools which will help you while coding in Go. I'll not take time on this part, because if you are familiar, you can take a look at my slides later. But compile bench is one of the main component, a main tool you can say. And CMD compile contains the main packages related to the Go compiler. And I've mentioned everything. I'll not get into it detail because it's just 15 minutes of time we have. And all the resources I've mentioned here related to the compile, bench, perf, all the additional tools which I've mentioned, and also the first resource is related to a Go compiler introduction. It has every single thing, and I have taken my slide, created my slide through that. And thanks a lot for coming and attending my slides talk. If you are interested in viewing my slides at this moment, you can just go to slides.com, Zainal, FOSSASIA, Hanoi. You will get the whole slides, resources, everything at a single place at there right now at this moment. And thank you so much. If you have any questions, do let me know. That's all from my end right now.